Hello and welcome to another lecture for ECE 205. In this lecture, we're going to focus on solving a particular class of differential equations, and our goal is to try to solve them for kind of as broad of a class that we can. So without further ado, let's jump straight in. Okay, so we're going to focus on solving differential equations of this form. Okay, so here this function p naught of x, this is assumed to be not identically zero. That is to say, it's non-zero for some point x. And further, we assume that this function p naught of x, p1 of x, and this function f of x are all continuous on some interval. So before we try to solve this equation, let's introduce some nomenclature and talk about some new concepts before we get into the nitty-gritty details here. Okay, so first, in terms of our nomenclature from lecture 1, just notice that equation 1 is going to be linear. So linear because there's no terms like y squared, y cubed, y prime times y, anything like that. First order, and here first order since the highest derivative of y that I take is 1, differential equation that is homogeneous if and only if this function f of x is exactly equal to 0 for all values of x. Now, let's also note that I kind of have a special case sitting here that's kind of nice. If f of x is identically equal to 0, then pretty trivially, y of x is equal to 0 will solve this equation, right? If this is just 0, then on the other side, I'm going to, if I plug in y is equal to 0, I get 0 for this term. When I take the derivative, I get 0, so I'll also get 0 for that term. Okay, and this solution has a particular name. We call it the trivial solution. So any solution other than this y of x is equal to 0 would then be called a non-trivial solution, okay? And again, it's trivial solution because it's always going to be a solution if f of x is equal to 0. Okay, so our goal again was to try to solve this equation. So before we go about trying to do that, let's introduce a concept called the general solution. So the general solution to equation 1 is a particular type of solution, namely it's going to be a solution, say, y sub gen of x comma c, where c is an arbitrary parameter, such that two conditions hold. So for the first condition, for any fixed value of c in R, this y gen of x comma c is a solution of 1 on some non-trivial interval. So what this is really saying is that if you plug some fixed value of c into here, the resulting function y gen of x with that fixed value of c plugged in would be a solution to this equation. So next, the second property that I want a general solution to have is that if s of x is some solution to 1 on some non-trivial interval, just any interval wherever, then there will exist some value of c that I can plug into this y gen function such that s of x, the solution that I have, will be exactly equal to y gen of x evaluated at that value of c on that interval. Okay, so what is all of this stuff really telling me? Well, let's just take a second and go back to look at the idea of a direction field from before. Well, here, if I just focus on this example, you can notice that for this direction field, I have these integral curves here, and each one of these curves represents a solution to the differential equation, in this case, this differential equation down here. So a natural thing that we might want to do is to be able to get one single function, say y gen of x comma c, such that when I plug in various values of c, it will give me these various curves. That's precisely what the general solution does. So this first condition here is really saying for any fixed value of c, if I take this y gen of x comma c, then that will give me one of these curves here that solves the differential equation. So that's the first nice property I want. And the second property is saying, hey, if you pick one of these curves, say, let's just highlight and pick this portion here of, say, this curve from just, say, this point to this point on some open interval, then there will be some value of c such that that solution that I found can be written exactly as y gen of x comma c. Okay, so that's this whole idea of the general solution, is trying to encapsulate all of this information in one simple, nice function. So just for completion on the slide, This is to say that the general solution contains the information about all of the potential solutions to the differential equation in question. So now everything that I've just said here about the general solution to this particular differential equation 1 generalizes in the way that you would expect, and we'll discuss that when the time comes. Okay, so before we jump into actually trying to find the general solution for all of these differential equations, it can be useful to try to find the general solution for one particular differential equation. So let's look at a motivating example. So here we want to find the general solution of this differential equation, and then we want to use the general solution to solve this particular initial value problem here. So let's jump to Mr. Paint and get into the details here. So to solve this question, we're first going to try to find the general solution of this, and then after we have that general solution, we're going to use that to try to solve the initial value problem. So this begs the question, how do I find a general solution? Well, let's just recall from the definition of the general solution. A general solution to the differential equation in that example will be a function of x and c, where c is an arbitrary parameter, that satisfies these 2 points here. Okay? So it turns out that it's easier if we start with number 2 to say, hey, if I have a solution, it has to be of this form for some value of c. That's kind of what we find when we actually go to try to solve a differential equation algebraically. Okay, so let's look at this thing. So we could try to apply that method that we did earlier, where we try to isolate all the y terms on one side of the equation, everything that depends on x on the other side of the equation, and hopefully integrate it to get that to work. So let's do that here. Well, in order to do that, I first kind of want to divide by this x. That could be a problem, right? Because x could be equal to 0. So we're going to do that same trick that we did before, and we'll say if x is not equal to 0, then we can divide by x to rewrite the differential equation. So explicitly in words, we divide by x to rewrite the differential equation as, well, what would it simplify to? Well, this would simply be y prime is plus y all divided by x is equal to 0. Okay, so notice if x is equal to 0, this equation simplifies to y is equal to 0, which is just the trivial solution. So really throwing out this case doesn't actually hurt anything on the way of trying to find this general solution. Okay, so now the next thing I would want to do is ultimately I want to get these y terms together. So I'd want to divide this whole expression by y. Well, that potentially poses an issue, right? So if I want to try to divide this by y, it better be the case such that y is not equal to 0. Well, to do this, what I'm going to do is I'll assume that y is not the trivial solution. If y isn't 0 everywhere, then since y is going to be a solution to this equation, that I want it to be, it needs to be differentiable and thus continuous. That means that on some open interval, y of x will not be equal to 0. So on that interval, this whole thing implies that y prime all divided by y is equal to minus 1 over x. Again, divide by y, subtract off the 1 over x. But remember, this is only true on the interval, or a interval, such that y of x is not equal to 0. Okay, so far I've made the assumption that x is not equal to 0, and y is not equal to 0. Those are fair assumptions that I can make, and in the end, I'm hoping, and it turns out that it is the case, but we're hoping that we can recover the trivial solution as one of those values of c in my general solution that I'm going to find. Okay, so now that I have this, I can simply take this thing and integrate both sides. So if I put that in a purple box, then this purple box implies that, well, once I integrate both sides, the left-hand side will simply give me ln of the absolute value of y, and the right-hand side will simply give me negative ln of the absolute value of x, plus some constant that I will call k. Again, note, I don't include the arbitrary constant on the left-hand side since it's already on the right-hand side. Okay, so let's call this solution green. Okay, so now this thing is what my solution would look like, but I really want to solve this thing for y. So how do I go about solving this for y? Well, we've done that before. I can take e and raise e to each side of the equation. So from here, this directly implies what? Well, e of the absolute value of ln of the absolute value of x or y is simply going to be equal to e of negative ln of absolute value of x plus k. Okay, so now on this left-hand side, or this right-hand side here, I can simplify this directly by noting, hey, this is just going to be e to the k times 1 all divided by e to the ln of the absolute value of x. And again, this e to the ln of the absolute value of x, that thing is simply going to be equal to x, right? So this all simplifies to e to the k all divided by the absolute value of x. Okay, so I'll clean that up and we'll come right back. Okay, so same work that I had before, just written in a little bit more of a cleaner framework here in terms of the page. So all of this thing is really just telling me that the absolute value of y, so this is all implies that the absolute value of y is just going to be equal to e to the k all over absolute value of x. Okay, so in my general solution, I don't want the absolute value of y. I just want y, right? So how can I get rid of this absolute value? Well, previously I was very hand-wavy and I just called e to the k some arbitrary constant c that could be positive, negative, or 0 and said I was good to go. Let's be a bit more precise here. So explicitly, the right-hand side of the equation and the left-hand side of the equation are both positive. They do not change sign. So if I want to rewrite this thing and say that this implies that y is equal to, say, something c over x, this would be the form if I just drop the absolute value, I need to be careful to determine exactly what c is in terms of this e to the k, and maybe plus or minus or some other things floating around. So let's see what c would need to be for two different cases. The case where y is positive and the case where y is negative, or really non-negative and non-positive. Well, c is going to be equal to, well, if y is greater than 0, then here this absolute value of y can be replaced strictly with the y. And pretty clearly, c will simply be e to the k, okay? Because I don't have a negative floating around. On the other hand, if y is less than 0, then this absolute value y simplifies to negative y, and I need to pull the negative through. So c would then be negative e to the k for that case. Okay, so if I box this in kind of a nice green color, this is my solution that I have found with the assumptions that, again, x is non-zero and y is non-zero. Now, we can't relax this assumption that x is non-zero, right? Because in the case where x is non-zero, we don't even have a differential equation in that case. But noticing if we relax this restriction on c being of these two forms and let it be some arbitrary real number and just consider this new y-gen of x comma c to be this function here that's just c over x. So this function y-gen of x comma c is what I'm proposing will be the general solution. So what have I shown by doing all of this work? Well, if I go back up here, I've really shown that if I have some solution on some non-trivial interval, then there's going to exist some c such that my solution is equal to this. Why have I shown this? Well, I've shown, hey, this thing is reducible exactly to these equations here, which simplifies to this. So if I have a solution, it has to be of this form. On the other hand, I now need to show that for any fixed value of c, this y-gen that I found is a solution to this on some non-trivial interval. So how do I go about doing that? Well, I simply take this and I plug it into the equation and show that it is always going to be a solution. So that's pretty trivial to do, so I'm not going to go through all the details here, but I will note that if you look at the text, this example was taken directly from the text. For the converse direction, all you have to do is simply differentiate this as follows, plug them into the equation, and lo and behold, yes, they add to give 0. Therefore, the part 1 of being a general solution holds. Okay, so I just want you to keep in mind that you do need to show both 1 and 2. Showing 2 is really the more difficult part. To show 1, you really just have to differentiate the function and verify that it works. And just for completion and to be a bit more exact, if I tell you to find the general solution, you can just get to this point and say, hey, there it is, I'm done. If I tell you to show that it is a general solution or prove that there exists a general solution, that's where you actually have to show the other nitty-gritty details for part 1. So just keep that in mind for assignments. Find means do part 2, find me the function. Show that it has a solution means 1 and 2. Okay, so now that I have this general solution, I want to use this to solve this initial value problem. And it turns out if I want to do that, all I have to do is take this expression here, substitute this ygen in for this y, and then simply find the value of c such that this condition is satisfied. So explicitly, what I would do is say, hey, y of 1, well, ygen of 1, that's just going to be c all over 1. That would need to be equal to 3. Oh, that implies that c is equal to 3. So the solution for the initial value problem, if I just called it y, it would simply be y is equal to 3 all over x. Okay. And here just cleaning up a little bit. So this technique is how I might want to go about trying to solve this particular equation, but my goal is not just solving this particular equation, but instead solving that general equation that I started out with. So let's look back to our main goal for this lecture. So explicitly, we now turn our attention back to the differential equation that we started out with. So this thing here, where this thing's not identically 0, and all these coefficient terms and the forcing term here are all continuous on some interval. So previously, in the previous example, to get rid of this p naught of x, I simply divided by p naught of x. So in general, that method will work on any interval such that p naught of x is non-zero. So like in the previous example, we can always divide by p naught of x on any interval where it is non-zero. And we're guaranteed that such an interval will exist since p naught of x is identically not identically 0, and it is continuous. So that gives me the existence of such an interval. Okay, so if I do this, this differential equation up here, dE number 1, can be rewritten in kind of a cleaner way to work with. So explicitly, it can be rewritten as y prime plus this p of x times y is equal to little f of x. So here, p of x is simply the quotient of p1 and p naught, and little f is simply the quotient of big F and p naught. And again here, I have to restrict the values of x that are under consideration to be the values of x such that p naught of x is not equal to 0. Okay, so in practice, this restriction isn't all that restrictive, again, since there is this interval where p naught of x is non-zero. Okay, so now my goal originally is to solve this thing, but since I can always do this process here by restricting to an interval where I even have an ODE, right? Because if p naught of x is equal to 0, the ODE isn't an ODE any longer, right? I can now get away with working with this equation 2 instead of that first original equation 1. Okay, so that's what we're going to start doing for the vast majority of the rest of the lecture. So now, while this function here does look like it's a lot easier to work with than the original function, at least on the surface, it turns out that finding solutions for all equations of this form for arbitrary functions p of x and f of x is still quite an intensive project, process, and it can be difficult to do just from scratch. So instead, what we're going to do is we're going to first focus on the case where f of x is equal to 0. Explicitly, we're going to focus on the homogeneous version of this equation. That homogeneous version of this equation has a particular name. We call it the complementary equation. So explicitly, for any non-homogeneous ODE, the complementary equation will be the homogeneous version of that ODE. Okay, so if I restrict our examination to this equation, well, it turns out that we can very quickly solve these types of equations, right? We did one example up here when I found the general solution for this by first dividing by x. And this solution method turns out to work in general for these type of equations. So let's give a theorem and then go through the proof of that theorem. So theorem 2.1.1 from the text: if p is continuous on some interval ab, then the general solution of the homogeneous equation, the equation that we had on the previous slide, on that interval will simply be given by c e to the negative px, where this p of x is simply going to be the integral of little p of x dx. And this is going to be any antiderivative of p on the interval ab. So you might be asking, like, hey, what do we mean by any antiderivative of p on this interval? Well, we got you covered there. That is to say that p of x has the property such that if I differentiate it, it's going to be equal to p of x on this interval. Okay, so there's that little fussiness where you have that arbitrary constant you can play with, and that's why we have this any antiderivative sitting here. Okay, so how would I go about proving this theorem? Well, really, you do the exact same work that we did for this example up here, but instead of having a particular function, in this case 1 over x, you leave that as an arbitrary function of x called p of x. Okay, so let's go through the proof that's given in the text. I'm not going to read the proof out directly, but instead we'll copy paste it and go through the key elements of the proof that you should know. So if I want to show that something is a general solution to some homogeneous equation of this form, I again, just going back up to the definition, need to prove that these 2 points in fact hold. And recall, to show that one holds is pretty easy. I take the proposed general solution, differentiate it, and plug it into the differential equation. So let's just briefly look at how proving one is done. Well, in this theorem, I'm giving you a proposed general solution. So all I have to do is differentiate this, plug it into here, plug it in as it is in for y, and then show that this would be, in fact, a solution. So let's look at how the text does this. Okay, so just copying out the beginning part of the proof. So here I want to differentiate y, so that's pretty straightforward. Here's the function I want to differentiate. And a straightforward application of the chain rule gives me that this would simply be negative capital P prime of x times the function as it was, so this term here, which then can be simplified, right? So what do I know about capital P when I take its derivative? Well, I know that P prime of x is equal to P of x on the interval of consideration. So I can simply replace this with this P of x on that interval. And from here, I can simply then use the fact that, hey, y is just equal to this. So I could say that y prime is equal to negative P of x times y. Well, that is exactly what I wanted to show, right? If I just take that expression that I had and I add the P of x times y to both sides of the equation, I get the differential equation that I wanted to find the solution of. Okay, so that is showing all the work to show this part one of being a general solution. Now, the next part is the one where it's a bit more complex. I need to take the differential equation and I need to solve it for an arbitrary solution and show that that solution has the form of my proposed general solution. Well, that's really just rehashing this stuff here. So let's just take a look at the proof in the text. So we first suppose that y is a non-trivial solution. Why do I make this assumption? Well, the non-trivial solution is recovered when I let c is equal to 0. And ultimately, in my process of solving the differential equation, I want to take this thing here and I want to divide the whole thing by y to separate the y bits from the non-y bits. Okay, so if y is a non-trivial solution on that interval, then I know that there's this open interval such that y has no zeros. So again, I divide by y, and my differential equation simply becomes this equation here. Pretty straightforward. Okay, from here, I then integrate both sides. I get this expression here. Here I'm using the fact that capital P is the integral or a antiderivative of P. So from here, I get my arbitrary constant. Again, that's my constant of integration. So at this point, I do the same trick where I take e and raise it to both sides of the equation. E of ln of absolute value of y, that's just this. E of the other side, that simplifies to this expression here, just like I had before. Okay, and now at this point, I use the fact that the exponential term here can never be 0 along with this term here, and then I just expand out the definition of the absolute value of y to solve for y as a function of this new c to get this form here, where again c changes sign depending on the value of y. Hopefully with the example that we covered, this is straightforward. If it's not, again, you can check out the proof in the text, which is exactly what I just went through here. And of course, ask questions on Piazza or office hours if you have particular questions on the details there. Okay, so one thing I want to note here, I don't want you to actually just memorize this expression, right? You could memorize that if I have a differential equation of this form, if I want to find the solution, I simply take it to be c e to the integral of p of x dx. You could memorize that, but for the vast majority of the topics in this course, if you just memorize this form of the solution, you're going to run into the issue where 2 months down the line, maybe during the final even, or 3 years down the line, whenever you need to solve these equations, you're going to forget this form of the solution. But this method, this whole process that we went through in this proof, is easier to memorize, right? It's a kind of natural way that you might want to try to tackle this type of problem. So I recommend to memorize the method, not the formula here or these particular theorems. But that said, you can use this kind of as a cookbook in some sense, where if I have a differential equation of this form, I find a solution of this form, evaluate the stuff. So just kind of a word of caution for the course, and ideally do memorize the process because that will let you get more out of the course. Okay, so let's continue. This theorem allows me to solve one entire large class of these type of differential equations, right? If little f is equal to 0, then I have a solution. So now what remains to be shown is, what if little f is not 0? How do I find a solution in that case? Well, it turns out that we can use the solution of the homogeneous equation to find the equation for the non-homogeneous equation. Okay, so natural thing you might ask is how? Well, we use a method, or a kind of one edge case of a method, called the variation of parameters. So what's the variation of parameters? How does it work? Well, we assume the ansatz that y is equal to u times y1, where y1 is a solution to the complementary equation, namely the homogeneous equation, and u is some differentiable function, okay? So what do I mean by ansatz? Well, in mathematics in general, and in particular for analysis type things, an ansatz is basically an educated guess for what a solution might look like. And then you go, hey, what if my solution looks like this? And then you check like, hey, if it looks like this, then it has to satisfy this equation over here. And then you can ultimately use an ansatz as a tool to find a solution, okay? So just a little bit of general nomenclature there. So again, the natural question to ask is, how does this help? Well, let's go over to Mr. Paint and examine how this helps. Well, let's write down the moving parts that I have here. So I'm just going to copy this over from the lectures and come back in a second. Okay, so we know that y1 solves the homogeneous version of the equation, and we're assuming the ansatz that y is equal to uy1, where u is a differential function. So from here, we want to ultimately find a solution to this non-homogeneous equation. Well, If I'm assuming I have a solution of this form, the natural thing to do is to take this and plug it into here. Okay, so let's do this. Well, y prime, if y is equal to this, then y prime is going to be equal to what? Well, here I have the product of two things, so I just use the product rule. So I'll get u prime times y1, and I know this u prime exists because I'm assuming that u prime is differentiable. This term right here. And again, I can make that assumption because it's an ansatz. I'm just guessing. I'm kind of taking a shot in the dark and seeing if it works. And here I'll get plus u times y1 prime. Okay, so I know this information here, and if I take these two bits of information here, this guy and this guy, together and plug it into here, what do I get? Well, that will imply that, well, y prime, that's just this expression here, plus p of x times y. Well, y again is this u times y1, so plus p of x, u times y1. And all of this is simply going to be equal to my f of x. Okay, I just made things worse. This looks awful. How does this possibly help? That was a bad idea. Oh, no, wait, let's notice something here. These two terms here have a u in common, right? So let's factor out the u and see what happens. Well, here, this would simply be u prime times y1 is plus u times this y1 prime plus p of x times y1 is equal to f of x. Okay, again, how does this help? Well, if I look at this term here, that's just the thing that I had over here on the left-hand side, right? And I know y1 solves this equation, so I know all of this is going to be equal to 0. This whole term goes away. That's nice. What that ultimately gives me is that u prime times y1 is simply going to be equal to f of x. Okay, and further, I know y1 is going to be the non-trivial solution because, again, I'm assuming that in my ansatz, right? Through the magic of fixing slides while doing the lecture, y1 is now a non-trivial solution to the complementary equation. So I assumed that in my ansatz, so I can now from here say this simply implies that u prime is equal to f of x all divided by y1 of x. Okay, so from here, from this equation at this point, I can integrate this with respect to x to solve for u, plug it into here, and I get my solution. Okay, so that is how this helps. By making this ansatz, I get an expression that I can solve for u, and then I can plug that in, and lo and behold, I get a solution to the homogeneous system of equations. Again, this method is called the variation of parameters, and we will see it throughout this course. Okay, so sticking this in the slide, that's the justification for why this helps. This is also available on page 35 in Trent if you want to see it kind of written out in a different way there. Okay, so now before we actually get into kind of doing this in general and turning it into a theorem, let's give an example of using variation of parameters to find the general solution of a non-homogeneous differential equation. That's also first order and linear. Those are kind of key things. This method, as of now, only works within these type of equations. You can generalize it, and we will, but yeah. Okay, so let's go over to Mr. Paint and ask him how we solve this. Well, if I want to use variation of parameters to find a general solution to a non-homogeneous first-order linear differential equation, I first need to solve the homogeneous equation. So we first solve the equation. And what equation are we going to solve? Well, it's going to be the exact same equation that I had here. So y prime plus 2y. But it's going to be equal to 0 instead of x. So we know how to solve this. We could do it via the theorem that we had over here, this 2.1.1, simply just plug in to integrate. But instead of doing that, I'm going to do this by hand just to give you another example of solving this here. Okay, so this equation I divide through by y, assuming y is the non-trivial solution, to simply get y prime over y is simply going to be equal to -2, right? The 2, and I bring it over from here. So if I integrate both sides on this, on the left-hand side, I'm going to get ln of the absolute value of y. And on the right-hand side, what am I going to get? Well, the integral of -2 is going to be simply -2x plus my constant of integration. Okay, so now I raise both sides to the power of e, so this directly implies that y is going to be equal to, well, this will simply be some arbitrary constant, say c1. Make sure you use a different name than the constant that you use up here. So just through the magic of doing it later, I'm going to swap them because c is nicer. And that's just going to be multiplied by e to the -2x. Okay, so now when I want to try to use variation of parameters, I don't need all of these solutions, right? I only need one of them. So I'm just going to let c be equal to 1. Okay, so now through the magic of pausing the video and cleaning it up, I'll clean up this to make it a little bit more presentable, and then we'll go forward from here. Okay, so cleaning it up here, solve the equation, found my solution to the homogeneous equation, pick some arbitrary constant other than 0, because it's the trivial solution, to get some non-trivial solution to the homogeneous version of this equation. Okay, so now what do? Well, I make that ansatz, right? We assume that I'm going to try to get a solution of the form y is equal to y1 times u. Okay, so if I make this assumption, I again get from here that this implies that y prime is simply going to be equal to y1 prime times u plus y1 times u prime. Okay, so now when I plug this into the differential equation, it simplifies it, right? So the left-hand side, what would that simplify to? Well, if I just kind of steal from what I've already done in the lecture slides, this y prime times p of x of y, it's going to simplify in the same way that it's simplified up here in the kind of more general case. So I don't actually have to compute all those intermediary steps. I can leave it as arbitrary functions and just simply notice that the left-hand side of the non-homogeneous equation will simplify to u prime times y1. So explicitly for this case, the ODE will become u prime y1. So explicitly u prime y1 is just this function here. So u prime e to the minus 2x is simply equal to the right-hand side of this non-homogeneous equation. So in this case, x cubed e to the minus 2x. Okay, so my goal here is to solve this for you. So to solve this for you, I'm going to do the exact same thing that I did over here in this particular case. I'm simply going to divide by y1. So in this case, y1 is this e to the -2x. So e to the -2x is never 0, so I can simply divide by it. And this gives me that this, this implies that u prime is simply going to be equal to x cubed. Okay, so now since I have u prime is equal to x cubed, that I can integrate. So here, if I integrate both sides with respect to x, I simply get that the integral of du is going to be equal to my x cubed dx. Okay, so from here, this is straightforward to compute. From here, I know that u is going to be exactly equal to x to the 4th over 4 plus some arbitrary constant that I'm going to call c. So note, I kind of used c over here for this other sub-problem. That c is kind of confined over here because I don't have the c once I picked my particular solution to the homogeneous equation. So I can use c at this point. But just be careful with the scope of your variables. Okay, so now that I know what u is, what do? Well, I just simply multiply these things together. So my solution, and I will do it in green, my solution is thus going to be y is equal to, well, it's going to be y1 times u. So this is simply going to be e to the minus 2x times parentheses x to the 4th over 4 plus some arbitrary constant c. Now, if you wanted to, you could expand this out, but that is our final answer here. Okay, so this method does work here. It does work in general. So let's go back to our slideshow to end the lecture here. Okay, so again, this is example 2.1.5 in Trench if you want to see it written out there. Okay, so let's give a TLDR of what we've learned in this lecture. So if I give you a differential equation of this form, that is a linear first order non-homogeneous differential equation, you can apply the following algorithm. So the first step is to find a solution to the complementary equation. So recall the complementary equation is this equation here, but in the case where f of x is equal to 0. So how do I find a solution to the complementary equation? Well, I isolate this equation for y prime over y, and I find a function y1 such that y1 prime over y is equal to negative p of x. That's the separation of variables step that we've done a few times in the last couple of lectures. So note here, when you go to solve this for y1, you need to integrate. And when you integrate, you're going to get a constant of integration. That constant of integration can be any particular number, so just pick the value that makes it kind of the easiest function to work with. Okay, so after we do this, we then make the ansatz that y is equal to u times y1. Okay, so by making this ansatz, we're assuming that I can find a solution of this form, and I'm going to plug that in and try to get a solution. So when we make this ansatz and plug it into this homogeneous or non-homogeneous equation and simplify it, that will simplify simply to the equation u prime is equal to f of x divided by y1 of x. Okay, once I have an equation of this form, I then want to integrate this to solve for u. We'll again get an arbitrary constant, but this constant you can't pick to be a particular value because that's the constant that you get for your general solution. So from here, we then just simply use this solution for u to obtain the solution for the original equation. Okay, so explicitly, we take this assumption here, we just take the function for u that we found, plug it in, and then we take the function for y that I found up here and plug it in. Okay, so that's all there is to this. Now, if on the other hand, I gave you something like this and asked you to solve it, I can clearly do that step where I divide by p naught of x and restrict my domain of interest to some non-trivial interval where p naught of x is non-zero. Okay, and once I do this, this equation would be put into the equation of this form up for here, and then I can apply this algorithm for the method of variation of parameters. Okay. Pretty straightforward and to the point, right? Right? Well, generally speaking, the only thing I know about p of x in this f of x are that they're continuous functions, right? That's my kind of starting assumption. So I know if they're continuous functions on a finite interval, I can integrate them, but I don't necessarily know if I can actually get a closed form for the integral of it. So sadly, while this method will give me a solution, it is a proof that solutions to this equation exist when you kind of clean it up a little bit. Next slide. It doesn't necessarily give me an analytical form of the closed solution in terms of standard functions. So to be explicit, note that sometimes we might not be able to actually write the solution in closed form, and we'll need to leave the solution in the form of an integral. Okay? Generally speaking, if I give you an arbitrary, completely random ODE of this form where p and f are continuous, you won't be able to integrate it. Okay, so for one example of that, see example 2.1.7 on page 38 of the text as a good example of where you can't integrate it analytically. Okay, so just like earlier when we solved the homogeneous equations and we had a kind of methodology that we found to solve the equations explicitly, this method that we used here where we got all the y's together, all the things that depended on x on the other side of the equations and then integrated it. And we could use this method to turn that into a nice theorem for when we have a solution and for the functional form of that solution, and kind of a plug and chug theorem, so to speak, of if the ODE is of this form, then all you do is evaluate this integral to get the solution. We can do the same thing with this algorithm here. So for the final thing for this lecture, let's turn this algorithm into a theorem and kind of skip over the proof of it. Okay, so the variation of parameter algorithm directly leads to this useful theorem. So suppose P and F are continuous functions on some open interval from A to B, and let y1 be any non-trivial solution to the complementary equation here on this interval. Then we can say two things. One, the general solution of the non-homogeneous equation, so this equation here on this interval, can simply be found by this expression here. So ultimately, how do we find this expression? Well, all we do is go through this process that we already did over here. We simply integrate this to solve it for u, and then we plug that into our ansatz, where for y1, we use the fact that we know an analytic solution to the homogeneous equation from theorem 2.1.1. And when you do that, that's where this functional form here comes from. Okay, and secondly, we know that if x naught is any arbitrary point in this interval, and y naught is an arbitrary real number, then the initial value problem for this non-homogeneous equation has the unique solution given by this quantity here. So how do you find this? Well, all you do is you plug in the initial value into this equation here, and you solve it for c. So when you do that, this is what you need it to be in that case. Okay, so there's a little bit of detail that you need to do to get this integral from x naught up to x. And explicitly, that's just picking which particular antiderivative you want to use here. Nothing super fancy. The proof for this, the formal proof for this, is given on page 40, but we've already given most of the work in the previous example that I gave, so I'm going to skip over the proof here just for lack of time. If you have questions, feel free to ask away and we can discuss the proof in office hours or parts of the proof that you might be confused on in Piazza. Okay, so that is it for this lecture. So I want you to read section 2.1, and I want you to look at practice questions 1 through 43 on pages 41 through 43. Now, I don't want you to go spend the time to do all of these practice questions. That's not strictly necessary. It's just these are a large list of questions that I'm suggesting you could look at to get more practice for solving equations like this. Okay, so just solve as many of them as you need to solve to kind of feel comfortable with the basic process of how to attack these type of differential equations. And then you can save some of them later for doing some practice for, say, the midterm or the final. Okay, so like always, I will leave you with a meme. So here's our meme. A solution y1 to the complementary equation of the first order linear ODE. Some function u, multiply them together, you get a solution to the non-homogeneous equation. Okay, so as always, well, actually it's the first time I've said it, have a good weekend, and I will talk to you hopefully in office hours. If not, you'll hear from me during the next lecture. Have a wonderful day, and I'll talk to you later.